Hello everyone, today let's take a look at another sets question, quantipus number 20, which we can solve with just basic inclusion-exclusion. Okay, so we have a school of 100 students and we have the information about the enrollment in 3 different classes, math, art, and karate, and then it's asking us what is the probability that a random student from this class is enrolled in none of the 3 classes. Okay, this is a drawing of our sample space, right? There's going to be 100 students within this box here, and the K, A, and M represent karate, art, and math. So the 100 students could be anywhere within this box. If they're in here, they're only taking art. If they're in here, they're only taking karate. If they're in here, they're taking both art and karate, and etc. So we're basically trying to find the number of students who are enrolled in none of the 3 classes, and that means you're going to be somewhere out here. So let's see what the question tells us. It says 33 students take math. That means that the magnitude of this blue circle here is 33. Now 40 students take art, so there's going to be 40 students within this red circle. And 20 students take karate, so there's going to be 20 within this orange circle here. Then it tells us that 10 students take both art and karate, so what does that mean? Well, it's just saying the magnitude of A intersection K is equal to 10, so where does A intersect K? Well, it's just going to be this black circle here. Okay, so magnitude of 10 here, and then it tells us that 5 students take both karate and math, so that's just going to be the magnitude of this here. We'll call it 5. And it tells us 10 students take both math and art, so right here. And then it tells us that 3 students take all 3. So we know that there's 3 smack dab in the middle right there. Now, this is all that we're given. Now, we're trying to find the number of students that are not in either of these 3 bubbles. We know there are 100 total, so we're just going to take 100 and subtract off the union of the sets A, K, and M, right? All that's saying is let's count everything inside of these 3 bubbles and just subtract it from our total, and that'll leave us with everything outside. Now, we know how to solve for the union of a bunch of sets, and we're given all the necessary information, right? We're just going to use the inclusion-exclusion. So we'll go on to do a lot more of this inclusion-exclusion stuff, especially in combinatorics. We'll even end up proving it. But right now, all you need to know is how it makes sense for 3 different sets. If you actually plug in our numbers here, we're just going to get 33 plus 40 plus 20 minus 10 minus 10 minus 5, and then plus 3, and that's going to end up equaling 71. Now the way you do it just by looking at the Venn diagram is, okay, I have 3 in the middle and I have 10 in this outer circle here, so there must be 7 here, right? 10 minus 3. And then you'd say, okay, I have 5 in this salmon colored circle and 3 in the middle, so there must be 2 here. I have 10 in the black and 3 in the middle, so there must be 7 here. Then you say, okay, I have 40 in the entirety of this circle, and then I have how much? 7 plus 3 plus 7, 17 in the middle, so I must have 23 out in this area. And you do the same thing here. I have 12, 20 total, so 8 over here, and then I have how many? 7, 8, 9, 10, 12 here, and I have 33 out here, so 21 over here. And now we've broken it down into disjoint components, and we can just sum them up, right? 21 plus 2 plus 3 plus 7 plus 7 plus 8 plus 23 will also give us 71. But it's kind of inconvenient to do this every time, right? So we just want to use the inclusion-exclusion principle, but why exactly does it work? Well, I'm trying to calculate the union of 3 sets, so I'm just trying to sum every single element that exists within any of these 3 sets, and I want to count each one time. But notice when I sum up the magnitude of A plus the magnitude of K plus the magnitude of M, right? That's going to be 40 plus 33 plus 20. It's going to give me 93. But I ended up overcounting a bunch of things, right? The magnitude of this green circle right here belongs both to A and to M. So it was counted both in the 40 and the 33. So when I summed them up, I overcounted this once. Similarly, the intersection between K and A, this black part here was overcounted because the 10 belongs both to this 40 and to this 20. So we overcounted it once as well. And same with this salmon colored part, right? It was both included in the 33 and the 20. So every single one of these pairwise intersection was counted twice, even though we only wanted it to be counted once. And that's why we subtract off every pairwise intersection. And when we do that, which in our case was minus 10, minus 5, minus 10, well then now all of the pairwise intersections were counted one time, which is what we want. But notice that the triple intersection, this 3 in the middle, was originally counted 3 times in our 93 count because it belongs to all 3 of these sets. So the triple intersection of these 3 sets was counted 3 times in this number here. But now notice that in our double intersections, well, 3 is obviously included in all 3 of these, right? So now we are subtracting off the triple intersection again here. We're subtracting it once, we're subtracting it once here, and we're subtracting it once here. So it got counted 3 times and subtracted 3 times. But how many times do we want to count it? Well, we just want to count it 1 time. So that's why we add back on the triple intersection. So now everything is counted once. So we add back on 3 here and we get 71. So now we know the magnitude of people that are in any of the three classes, right? It's 71, but we were trying to find the magnitude of people who are in none of the classes. So we take 100 minus 71, and that leaves us with 29. So there are 29 students who are enrolled in none of the classes and 100 total. So what is the probability that a randomly chosen student is enrolled in none? Well, it's just going to be 29 divided by 100, or 29%.